Good evening, everyone. It's a great pleasure to have our next speaker in the algebraic special functions and number theory seminar, my very good friend, Arvind Ayyer from IISc Bangalore. So Arvind has done great work in probability, combinatorics, many areas, and he has published in very good journals like Duke, IMRN, Transactions, Advances, etc. Today, he'll be talking on a new combinatorial formula for the modified McDonald polynomials. Over to you, Arvind.
Thank you, Atul, and thanks to Gaurav also for this invitation. What I am going to do is present some joint work with Olya Mandelshram, who's at Waterloo, and James Martin, who's at Oxford. This is a part of two series of works, one of which has been published in this Algebraic Combinatorics Open Journal last year, and one is has been submitted. So my goal in this talk is to focus on this first work, which is more closer to special functions and symmetric functions. And if time permits, I will go to the probabilistic side. So I'll start with the then spend some time on this new combinatorial formula that we have, and then I'll explain some nice Q series that comes up in our work, for which we needed to prove some identities, which you can think of purely in terms of Q series. And as I said, if I have time, I will explain this work. Okay, so let me just set some notation. So suppose x1, x2, etc. are a family of commuting indeterminates. You can consider the algebra of symmetric functions in these variables, potentially infinitely many variables, where the coefficients are rational numbers. And for this space, there are several natural bases. So this is a vector space in particular. So you have, you can talk about natural bases. So these first four bases are classical. I mean, by classical, I mean, dating back to Newton, for example. So the monomial symmetric functions, which are just the simplest thing, you take a monomial in these variables and you symmetrize it. So you get a and so they are all indexed by partitions, which I hope this audience I don't have to explain. So these are just weakly decreasing sequence of integers with finite sum of positive integers. So that forms so the monomial symmetric functions, you take a monomial and you symmetrize it, so you will get something indexed by partition. There are other standard bases. One is the elementary symmetric functions, the complete or homogeneous symmetric functions, and the power sums. So these four are classical. The Schur functions are modern in the sense they came up in the 20th century, studied because of its connections to representation. So I won't say much about the Schur polynomials, except here and there. But we are interested in a two-parameter generalization of these things, which are called the McDonald polynomials. So now, instead of taking your coefficients to be rational numbers, you take the fraction field in these two variables, q and t. So you have two extra indeterminates, q and t, and your coefficients are allowed to be rational functions in these. And the McDonald polynomials were simultaneous generalization of several different families of symmetric functions, which were in the literature coming from various different motivations. And in one shot, McDonald generalized all of them at the same time. So again, they are indexed by partitions. X stands for x1 up to xn, or even potentially infinitely many variables, and q and t are two other parameters. By the way, McDonald unfortunately died last year in August. So I think there is a plan to honor him in the coming FIPSAC in Germany. Okay, so anyway, there are simultaneous generalization of Schur polynomials, Hall-Littlewood, Jack polynomials, even Whittaker functions which come in number theory. It's just immediately generalizes all of them. And to define them, you need this inner product on symmetric functions, which are determined by the power sums. So the power sum symmetric function, which I had defined in the first slide over here. They are orthogonal. So there's this delta lambda mu times this other factor z lambda, which is product. I mean, which is a certain product of factorials, which is I mean, it's a well-known sequence of numbers times this ratio, this potentially infinite product. So 1 minus q to the lambda, 1 minus q to the lambda.
So what are p sub lambda, p sub mu again?
Sorry, so lambda is this partition, right?
No, yeah, p sub lambda. It's just a
P sub lambda are the power sum symmetric functions. So so maybe I can define it. So Pn, the nth symmetric function, is just x1 to the n plus x2 to the n plus x3 to the n and so on. Right? So that is Pn for an integer n. And P lambda is just the product of P lambda 1 times P lambda 2.
Okay.
Okay, so that's all. It's one of the simplest.
Okay.
Product in terms of P lambda and Q lambda, P lambda P mu, then you can therefore define it for any two symmetry. Okay. So this inner product looks funny. I mean, there's no, why should you have it this way? But there are strong, good motivations for having this. And so I misspoke earlier. So I said this is an infinite product, but of course it's a finite product because lambda and mu will have finite sets. So okay, so once you have that inner product, I can define the McDonald polynomials. So they have a monomial expansion. They have a expansion in terms of the monomial symmetric functions, and where these u lambda mu's are again rational functions in Q and T. But the important condition is that mu is less than or equal to lambda. So the only terms that contribute over here are less than or equal to lambda, and this less than or equal to is a standard ordering on partitions known as the dominance order. And also the diagonal term is 1. So you have this as one condition. And the second condition is that they are also orthogonal with respect to the same inner product. So just like P lambda, the power sums, the McDonald polynomials are also orthogonal. So it's highly non-trivial that these two conditions together will imply both existence and uniqueness of the McDonald polynomials. The issue is that this is an overdetermined system of equations, and somehow it's not at all obvious that you will have a solution and the unique solution. So McDonald proved that the solution is unique by explicitly constructing some operators for which these are the eigenfunctions. But this is a deep result. So just to show you how complicated these polynomials are. So here I just take 3 variables, okay, x0, x1, all partitions of size 3. So this first part, I have grouped together terms with the same monomial corresponding to m lambda. So these 3 terms correspond to m3, the partition. Then you have this ugly factor times m21. Hi, Atul, can you hear me?
Yes, in between, I think it had froze.
So I got a notification that my internet connection is unstable. So I was saying that, so let me just repeat what I said.
Sure.
So I'm expanding P lambda in terms of the monomial basis. So the first 3 terms correspond to of the partition 3. The second term is this with coefficient 1. This is part of the definition. Then this ugly polynomial rational function in Q and T times an even uglier polynomial rational function in Q and T times M111. Okay, this is how it's going to. And P21 will have only the latter two terms. And the last one will just be this, because there's nothing below it in dominance. Okay, so this was introduced by McDonald, and these, as you can see, are quite complicated. There's a more combinatorial version of the McDonald polynomial, which are called the modified McDonald polynomials, and they are obtained by certain plethism, which is a complicated operation on symmetric functions, which I don't want to get into and which will not be relevant. But I can say, okay, it will be relevant in the sense I should. So this square bracket here denotes plethism. Okay, so I don't exactly want to get into what it is because it's a bit complicated to define. But I suffice it to say, one is an expansion of in when you transform the variables by this in this way in terms of the Schurs, where the restriction is that the summands are only those partitions which are greater than or equal to lambda prime, the conjugate in dominance order. And a similar thing for when you transform it by this Q. And the inner product of this modified McDonald polynomial H tilde lambda with S of the with the Schur function indexed by the singleton n is 1. And this is essentially, after a lot of algebra, it's essentially a reformulation of McDonald's axiom. But okay, as I said, all of this is completely opaque, but I won't deal with it. But just to show you the same the same modified McDonald polynomials now for the same example with 3 variables and partitions of size 3, you can see that the coefficients are now rational, polynomials with integer coefficients. So you again get M3, you get this polynomial in Q times this M21 and this polynomial in Q times M1. Okay, but here you lose the triangularity. But here you gain much more in the sense that, as I said, the coefficients are now are polynomials in Q and T, and with integer coefficient, with in fact non-negative integer. And if you stare a little bit, you can see that the first and the last are very related. You see, here this is Q squared plus Q plus 1, here is T squared plus T plus 1, and here this same thing in Q appears as T. Okay, so there's some strong connection, and this is the symmetry I was pointing out. And here, if I interchange Q and T, I get the same thing. Okay, so you can see that something is going on. And so these are so let me summarize some properties well known. So the coefficients are polynomials with H tilde lambda related by interchanging Q and T. This is precisely the symmetry that I observed in the last slide. Okay, so they also have, if you expand them in the Schur basis, they have this coefficients. These are related to the Koska-Fuchs polynomials. And, you know, one of the biggest open problems in this area is to prove that the Koska-Fuchs polynomial has no negatives. This has been a long-standing open problem. Okay, so there are many combinatorial formulas for the modified McDonald polynomials. So one of the biggest breakthroughs was achieved by Hagelin, Heyman, and Löhr in his influential JAMS paper in 2005, where they gave a formula for H tilde as a sum over tableau with 2 statistics, match and inf, which I will explain very soon. In a different direction, Kortel, Mandelstam, and Williams, they built on earlier work and gave a combinatorial formula for the p lambdas, the original McDonald polynomials, in terms of some tools which were useful in describing a stationary distribution of a certain probabilistic process, a stochastic process. And independently, these 5 authors gave a formula for H tilde lambda, again as a sum over tableau, with these same statistics margin in, but with much fewer terms. So, complexity-wise, this was faster. And separately, Garbali and Wheeler, they used integrability ideas from the theory of integrable models to give another combinatorial formula in terms of colored paths in 2 dimensions. But that is something I will not talk about. So our first motivation is a conjecture of these 5 authors, where they said that H tilde lambda could have another formula in terms of the same old statistic match, but a new statistic that we call Quinn. And that's what I want to spend most of the time on. Cortell, Mandelstam, and Williams. Oh, is it unstable again, Atul?
So in between, it's freezing, but only for like 2 seconds or so.
Okay. Do you want me to repeat something?
No, that's fine.
Okay. So thanks. So as I said earlier, there was a formula for p lambdas in terms of this interacting particle system, the ASEP. Can there be a similar stochastic process which is related to H tilde? So this is the second motivation, and that is the latter part of the talk, which I want to not go into. I mean, as far as possible. But yeah, if people are interested. Okay, so now I want to explain the new combinatorial formula. So this heavily builds on work of Hagelin, Heyman, and Loehr. So I will go over what they did with examples and explain where the difference is. Okay, so that's the motivation for the next few minutes. Okay, so and of course, please feel free to ask questions. Okay, so and I mean that seriously because the definitions are very complicated. So it's very easy to get lost. So suppose lambda is a partition in weakly decreasing order. So you all know the French notation and the English convention for drawing the Young diagram. This is unfortunately yet another notation, but don't blame me. This is not my fault. I mean, this is you can blame these Hagelin, Heyman, Loehr, for example. So they set this new convention, and we are stuck with it. So the diagram of type lambda, which will denote dg of lambda, is constructed by taking. So lambda is k part. So you take k columns, where the ith column has height lambda I, and you justify it at the bottom. So it looks like a building, So so this is the partition. Okay, just so that is in mind. Okay, it's again seeming to freeze. Okay. Okay, now a tableau of type lambda and this integer n is a filling. Sorry, this is a typo. It should be filling from 1 through n. You fill each n. Okay, and there is no restriction. So if you're thinking of standard tableau or semi-standard tableau, it's not like that. There's absolutely no restriction. You can do whatever you want. So for this previous example of lambda, I fill it and n
Could
equals.
you repeat the definition again? Like your voice just freeze.
Definition of what?
These new definitions like lambda n and like when you are defining the fillings.
Tableau, right?
Yeah.
Yeah, sure. So tableau is just a filling of the cells of this diagram of lambda with the entries 1 through n. So there's a typo here. I was saying that this should not be all natural numbers. It should be 1 through n. And in this example, I've taken n equals 3. Okay, so I fill it in any way that I like. I can put every single cell can be 1, 2, or 3. Okay, no condition.
Thank you.
Okay. Okay, so the monomial weight. So now I define a weight of such a tableau. Sigma is the tableau. Okay, so in this example, there are 5 ones, so it's x1 to the 5 and so on.
Yeah, I think we lost you.
Okay.
Yeah.
Sorry?
We lost you while you were explaining this last part.
Okay, so I was saying that since there are 5 ones, we have x1 to the 5, and there are 3 2s over here, so it's x2 cube and so on.
So, but if there is no
Weight of this.
if we can fill any of these squares with any of the numbers 1, 2, 3, then there are multiple polynomials that we get this way.
Sorry, say that again.
So you said that you can fill the squares with any of 1, 2, or 3, right?
Yeah, you can fill it in any way. Yeah.
There are multiple such polynomials that we get in.
Yeah. You'll get this monomial multiple times. Yes, of course.
Yeah.
Okay, so now I'm coming to the match statistic. Okay, so a descent in a tableau like this is a pair of entries u and v, where u is above v, and u has a larger entry than v. Okay, so for example, 3 is a descent because 3 is above 1, and 3, yeah, 3 is above 1 and 3 is larger. Okay, and the u in the same column. Okay, again, this is unfortunate notation because one doesn't think the leg should be below, but somehow this is their convention and we are stuck with it. So the leg is above. Okay, so the leg of the cell containing 3 is 0 because there's no cell above it. The leg of this cell containing 3 is 1. Okay, like that. Okay, and the major index now is the leg for all these descents. Okay, so for in this example, all the descents are marked in red, and this just contribute this one as leg 1, so you will get a 2 and 1 and 1, so you get total of 5. Okay, so I hope this example illustrates what the major index is. MAJ, this is denoted MAJ. Okay, this is the first important statistic. Okay, so the second statistic is really where it's quite complicated. So I'll go slowly. So suppose you can pick 3 cells in your tableau in this arrangement. U, V, and W. So V is directly below U, and W is in the same row as U, but to its right. I mean, there's no constraint on how far it has to. It can be arbitrarily far. Okay, and for now, forget about this slide, this bullet point. So I say that a triple like this forms an inversion if, as you read counterclockwise, you can find a location from which these 3 values will be increasing in increasing order. Okay, and there is a certain way to break ties. So I'll explain that in the next slide. So in case we are at the bottom row, okay, then this cell V does not exist and we only have U and W. In that case, we here is at U is Let me give you some examples of inversion. So look at this triple, 1, 1, 2, and 3 somewhere here. This forms an inversion because if I start from this cell containing 1, and I go counterclockwise, 1, 2, 3 is in increasing order. Okay. On the other hand, if I look at this example of a non-example, I cannot find any location from where I start and go counterclockwise and the 3 numbers are strictly increasing. So if I start here, I get 1, 3, 2. If I start here, I get 3, 2, 1. If I start here, I get 2, 1, 3. Right? So in no case I get strictly increased. So this is an inversion. So 3, 1, 2 is also. Okay. And there is a way of breaking ties. So rather than explaining, I'll tell you, if there are repeats, then the only way that contributes to an inversion is if these two cells U and V have the same number. It doesn't matter if it's larger or smaller. So both of these are inversions. But if I have equality here, for example, then it won't be an inversion. If I have an equality here, no inversion. Okay. So just to give you an example, so these two red ones. So then there are 3. Hello? Okay, so let me start again. So you look at these 2 ones. So the W can be any of these 4 cells. So only in this case do we not get an inversion. The other 3 will get an inversion. Okay, so that's why I have a red 3 over here. If I look at the first row, so look at 3 and a 1, then 3, 1, 2 does form an inversion because I can go 1, 2, 3. Okay, so that's this one. So similarly, I've done for every UV pair and I get 7 inversions. Okay, is this example clear? Are there any questions? I mean, this is the most confusing business in this business. Okay. So, so this is the theorem of HHL. So in sigma is the number, which is this complicated thing involving these triples. So that the theorem, the amazing theorem is that the modified Macdonald polynomial is given by a sum over Q to the major index T to the inversion X to the sigma. That was the monomial weight. Sigma. So if your X has infinitely many variables, you allow all possible fillings with natural numbers. There's no restriction. Whereas if you want to only look at x1 to xn, then you only allow fillings from 1 to n. Okay. And notice something strange here. The way the major index is very simple. It's just just this descents. But as I said, if lambda, then Q and T are switched, in which case bar switched. And that's highly non-trivial. I mean, there's no obvious way to see that these switching Q and T and changing lambda to lambda prime will give you the same thing because they're doing very different things. Okay. Combinatorial understanding of this property that I said earlier. Okay, so now I want to present the new formula, and this is very, very similar to the INV statistic, but not. So earlier we had these gamma triples where we have 3 cells where U and V is directly below U, and W was in the same row as U to its right. But now W is on the same row as V to its right. Okay, this is the only difference in the placement of the cells. Okay, forget about degenerate triples for now. So now we say that this triple forms a Q inversion. Again, if the entries increase as you go counterclockwise, you can find a location from which if you go counterclockwise, the entries increase slightly. And there's a way of breaking ties, which I don't want to get. So examples of Q inversions is exactly as before. So 1, 2, 3, because I start at 1, I go 2 and 3 counterclockwise. Similarly, 1, 2, 3. As far as breaking ties are concerned, it's the same rule as for the inversion statistic. If U and V have the same entry and W has a different entry, only then you get a contribution to the Q inversion. Okay, and non-Q inversions are the same way. If these two are equal, this and this are equal, but this is not, you don't get. And if all three are equal, also you do not get. Okay, so the degenerate case again occurs when U is not present. So in that case, V and W are in the topmost row of the tableau. And in that case, you get a contribution when the entry in V is strictly less than the entry in W. Okay, so this is the opposite of what happened for the inversion. So you have a smaller entry to the left of the larger entry. So if you think about it in terms of words, this is a non-inversion or a co-inversion. Okay, so going back to the same example tableau. Okay, should I repeat the last sentence? I mean, I was just saying that this is the opposite of the in statistic in the degenerate case, because they are in the correct order. So V is before W and sigma V is less than sigma. Okay, so going back to the same example now, and this L triple involving these two U and V, then W can be any of these 6 cells, and only 4 of these contribute where this is not equal to 1. So that's why this red. And for the same tableau, you had 7 inversions, but you have 12 Q inversions. Okay, and we'll let Quin be the number of Q inversions. Okay, so if you sort of got an idea of how in works, Quin works very similarly, but not the same way. And why Quin? Because this is a play on words. So Q over here is the English word Q, Q-U-E-U-E, because this will come from some multi-line Qs in the statistical mechanics model. Right, so it's a cheap pun. Okay, so our theorem is that the modified McDonald polynomial is given by almost exactly the same formula as Hagelin, Heyman, Ler, except that T, it's not T to the inv, it is T to the quinv. So, and Q to the match is exactly the same. Next to the sigma is also the same. So somehow this formula suggests that you should be able to sort of locally replace the inv by a quinv in some simple, you could do some flip, right? I mean, in one case, you had these gamma triples, and in the other case, you had L triples. So maybe there's some simple operation you could do. But we have tried all that. I mean, it's highly non-trivial. I mean, there's no obvious bijection that will prove this. Okay. So as I said, the inv and quinv statistics are similar, but we do not see how to go, and we cannot see any easy bijective. The only bijective proofs we have come up with are in some kind of trivial cases where you have 2 rows or something, where the diagram has height at most 2. I mean, in which case everything is easy, but or can be worked out. But in general, we just don't know how to see this. Okay, so let me give you one full example. This is the partition 2, 1, 1 in 2 variables. So you can fill it since each cell can be filled with either 1 or 2, and there are 4 cells, so you have 2 to the 4, 16 possible tableau. So in red, I'm showing you the quinv statistic, and sorry, in black I'm showing you the quin, and in red I'm showing you the in statistic. So for these cases where all the entries are the same, there's no contribution. Neither the match nor the quin contributes. Clearly, because there's no descent, and no triple can contribute because all entries are equal. Okay, so this is easy. Now, when you see the tableau contributing to x1 cubed x2, that means there are 3 1s and 1 2. And there are 4 possibilities because four choices for where the 2 can be placed. And now you see they don't quite match. So here I get q to the 0 t squared. So the degree of, the exponent of q is always going to be the same because that's the major index, which is the same for both. So just compare the t. So I have t squared here, t to the 0, t to the 1, t to the 1. Okay, that's the same. Here t to the 0 t squared. So this is the ulta of that. And here t to the 0. So there, it's not like, you can do some trivial flip. You can see here this 2 was at the end and here it's right here. So it's not just some obvious thing. Similar statistics, similar kind of argument. Similar kind of calculation for x1, x2 cubed. And when you have x1 squared, x2 squared, then again, the black and the red values add up to be the same. So for example, let's look at one example. So q to the 1, because this contributes to a descent, nothing else. And in the inf case, you get a contribution to inf from here, the degenerate triple, because 2 is greater than 1. But in the quinf case, you get no contribution. Okay, so because this is in the wrong order, and you get a contribution when there's a. But in all these cases, the sum is equal, and you get exactly this, and that is the h tilde 211 and 2 variables. Okay, so the proof is quite complicated, and as I said, it borrows ideas heavily from Hagler and Heyman-Lohr. So there is somehow having this in being replaced by quin just makes things harder for us. But in principle, there is nothing. All the ideas, the difficult parts are all there. So now I want to get to the Q series that all of you like. So the Q series will enter in the form of generating functions of words. So again, this is quite complicated, so I'll go slowly. So please feel free to ask questions. Roughly, capital N is some positive integer, and small n is some other positive integer, and we are considering words of length capital N in the alphabet 1 through small n. Okay, this is what we are doing. Moreover, we want at least three letters in the alphabet, otherwise this becomes trivial. And we fix alpha 2 to alpha n minus 1 such that so morally, what we'll be doing is we'll consider words with alpha 2 2s, alpha 3 3s, and so on, alpha n minus 1 n minus 1s. The only freedom we allow ourselves is in the number of 1s and the number of n's, the first and the last letter in the alphabet. We allow ourselves flexibility. So capital L is the total number of 1s and n's, small n's. Okay, so if this is confusing, we'll go through an example. So it's just to set the notation. So W sub k will be words in this alphabet where there are, as I said, alpha 2 2s, alpha 3 3s, and so on. We allow k n's and L minus k 1s. Okay, that's and the union of all these WKs will be the set, our entire set of words. Okay, so let's go through an example before it gets complicated. So I'm now looking at words of length 3, that is capital N is 3, in the alphabet 1, 2, 3. So small n is also 3. L is 2, which means there are two either ones or n's. I mean, the number of ones plus the number of threes is equal to 2. And the number of twos is fixed to be 1. This alpha tuple that I have. This is 1, this is fixed. Okay. So for example, when I said k equal to 0, that means there are no threes. So I have 2 ones and 1 2, and these are all 3. When k is 1, I have all of them 1. So I just get the 6 permutations in one line notation. And when k is 2, I don't have any ones. I only have 1, 2, and 2 threes, and these are these. Okay. Is the setting clear? And I know it's a bit notationally hairy, but I hope the idea is okay. Any questions? There's going to be there's a reason we need to do all this. I mean, this is part of the proof of that formula. Okay, so remember I spoke about co-inversions. So co-inversion in a word is a pair ij such that I is less than j and wi is less than wj. So it's the opposite of an inversion. So they are in the right order. Okay. So for example, 1, 2 forms a co-inversion because it's in the right order. And similarly, this one and this 2 forms a co-inversion. Like, okay. And so given a word w, co-inv of w is the number of such co-inversions. Okay. And now I define a new statistic, which is where, can you hear me? Yeah, okay. So now I define a new statistic, which is quinv, which is co-inv of w plus this k choose 2. So where k is this set where w belongs to. So here k was 0, 1, or 2. So quinv and coinv do not differ. I mean, there's no point of defining this if we were only looking at words in one particular level. Okay. But it's going to matter because we are going to compare things across different values. Okay, so to state the theorem, there's one last complication. Okay, so brace yourself. So now I'll put a superscript for wk, which will either be less than or equal to or greater than. So wk is all these set of words. Now I look at those for which the position of the leftmost n from the left is less than or equal to the position of the rightmost one from the right, but where you ignore all n's. Okay, so I know this is a mouthful. So let's go through an example. Okay, so again, same, well, not same, but similar example. So now words of length 4 in the alphabet 1, 2, 3, where there is 1, 2. Okay, and L is 3, therefore, and so I'm looking here W2 less than or equal to. So these are words in 1, 1, 1, 2, and 2 threes, because 2 is the number of n's, which is 3s. Okay. So these are all of them. And now let's look at something over here. So in this less than or equal to, the position of the leftmost 3 from the left, I should compare that with the position of the rightmost one from the right, ignoring all 3s. So here the position of the 3 is 1, leftmost 3 from the left is 1, and position of the rightmost one, and there's only 1, 1, from the right is also 1. So these two are equal. So this belongs in this because there's a less than or equal to here. Yes. So by this argument, you see that anything that begins with a 3 has to be here, because the position of the leftmost 3 is always 1, and the position of the rightmost one cannot be smaller than 1. No? So all of these will be here. Let's look at this example because this is non-trivial. So the position of the leftmost 3 is 2. But the position, okay, and the position of the rightmost one from the right is 4. But if I ignore the 3's, then it is also 2. So this is the equality case. Non-trivially. Okay. Similarly, here, for the same reason, this is 2 and 2. Okay. But now let's look at the greater than example. Here, the position of the leftmost 3 is 3, and the position of the rightmost one from the right, ignoring all 3's, is 2, which is less. Right? So this is greater. So position of the 3 is greater than the position of the 1. That's why it's okay. So for all of these cases, I have listed the quinv. Okay, I hope the example is clear. If not, please ask. Okay, so these are all the words in W2, and I have split it this way. Now look at this. So this is the magic that's going to happen. So if I sum over the quinv of all of this, and I factor it, I get this nice product formula. And if I if I sum the quinv for all of these guys, this is just q cubed times 1 plus q squared plus q cubed, and that factors in this. Right? So in each case, we are getting nice factorizations. So that is somehow the point. And that is related to our main theorem, which is the following. So take the union of all the wk less than or equal to's. Okay. I call that w less than or equal to, and similarly for w greater than. The claim is that there exists, so the theorem is that there exists a bijection between these two sets, which is highly non-trivial already, that there's a count that they are counted by the same, such that wk greater than maps to wk plus 1 less than or equal to in this bijective fashion, and the quinvs are equal. Moreover, the subword of the letters 2 to n minus 1 is preserved. So if I ignore 1's and n's, that subword is preserved. Okay, so we need this as one of the lemmas in our proof, but this turned out to be self-non. Okay, so let me give you an example. This is our was words with 2 1's and 1 2, and for that the quinv is just the coinv, because 0 choose 2 is 0. So because I had added this k choose 2, remember. So this is just the coinversion. So there are 2 coinversions here, 1 coinversion here, and no coinversion here. Okay. In the case of W1, also the quinv is the same as the coin, because 1 choose 2 is 0 also. So in this case, again, I have to count coinversions. So there's a reason I have split it this way. I'll come to that in a second. But let's just look at all the 6 words. So remember, let me just go back for just to remind you of this set. So these are these 3 sets I'm talking about. Okay, I've arranged them in these 3 columns. So in W1, we have again coinv, as I said. So this has the maximum 3 coinversions, 1 2 1 3 and 2 3, and this has no coinversion because everything is an inversion, and so on. So you calculate all of them, and you get this table. And for W2, you again calculate. This time there's an extra 2 choose 2, which is 1. So this guy has no coinversion, but I'll add a 1 because it's 2 choose 2 will get added. And similarly, so there's a 1 extra coinversion. I mean, quinv is 1 more than the coinversion. Okay, here. Okay, so now you notice that these 3 numbers are the same as these 3 numbers. These 3 numbers are the same as these 3. And what's going on? So in this case, when you have no 3, then everything is in the greater than set. And in this case, when you have no 1's, everything is in the less than or equal to set. Okay. But here this splits. So here there will be a W1 greater and W1 less than or equal to. And the point is that these three are precisely those with W1 less than or equal to. And so you see the bijective correspondence that these three will map to these three. And you see that the quin matches. And these three will map to these three. And again, you see that the quin matches. Okay, so if this were a co-inv instead of quin, this would be 2, 1, 0, and they would not match. Okay, so match it exactly, we have to shift the. And you can convince yourself that this belongs to less than or equal to, because the leftmost position of the leftmost 3 from the left is 2, and the position of the rightmost 1 from the right is, ignoring the 3, is also 2. Okay, so like that. And here it's the other way around. So okay, so this is the crux of this example illustrates the point of the theorem. So that is about to come. I mean, illustrates this bijection somehow. Wk greater maps to Wk plus 1 less than or equal to. But now I want to show you that not only are these, this is a bijection, we can compute generating function for each of those explicitly in terms of known q factorials and things. Okay, so I recall that the q number of n is 1 minus q to the n by 1 minus q, and the q factorial is the product of these, and the q binomial coefficient or the Gaussian polynomial is the ratio of these q factorials, and similarly the q multinomial coefficient is the ratio. Okay, all of this should be standard. So here's our main theorem, that if I take Wk greater than, and I sum over q to the quinth, I get this overall factor of q, which I can take outside, times the product of this multinomial coefficient and q multinomial coefficient, and choose L comma alpha 2 to alpha n minus 1, times the multinomial coefficient, q binomial coefficient L minus 1, choose k. And if I do it for Wq less than or equal to, I get something very similar. I get q to the k, choose 2, times this factor is the same, and here I get L minus 1, choose k minus 1. Okay, and now you can see that if I replaced k by k plus 1 here, this will match this. This is anyway the same, and this k minus 1 will be k. Okay, so and the proof uses standard things like the fact that inversion generating function of words in a certain alphabet. Okay, so let me be precise. So suppose I have words in the alphabet 1 through n with alpha 1 1s, alpha 2 2s, and so on, alpha n n's. Then if I take q to the co-in of those words, I sum, then I'll get precisely the q multinomial coefficient. This is standard result. And things like the Q-Chu Vandermonde identity is what we use. Nothing very deep in Q series, but somehow formulating this formulation people have not seen before, as far as we could see, and we get nice formulas for the generating functions. Okay, so I don't know. I don't have much time. So maybe I will not get into the exclusion process at all. It's okay to finish a couple of minutes early, I think. The audience will forgive me. So I just want to make one announcement, which is that we are going to have our second Meru so forget this poster. So we're going to have the second Meru Combinatorics conference from June 1st to 3rd in Graphic Era Hill University, which is in Bhimtal. And the website for the conference is over here. And it's open for contributor talks. And there'll be 2 mini courses, one by one of the seminar organizers, Atul Dikshit, and the other by from IIT Gandhinagar, and the other is by A.V. Jayanthan from IIT Bombay. So the details of the mini courses are also available on the website. The deadline for contributor talks is the end of this month. Okay, So I hope to see all of you there, and thank you for your attention.
Jayantan from IIT Madras, right?
Sorry?
I think Jayantan.
Oh,
is from
sorry. I
IIT.
should have been IIT Madras. Sorry, I don't know why I wrote that. Sorry, that's a typo. Jayantan is at IIT Madras. Sorry. Was that the question? I couldn't hear.
Yeah, I think that was the comment.
Okay.
Thanks. Thank you, Arvind, for a very nice talk. Are there any questions?
So I just wanted to ask, I mean, how is your formula any simpler than their formula? It seems to be the same. I mean,
Right. No, it's not simpler.
uh,
Right. No. I did not say that. Or at least if I said that, I did not mean to. All I was saying is that it's a different formula, and we don't see how to draw correspondence. I mean, if I'm allowed to be a little free, I would say that in our sense, our formula is conceptually more natural because it has this correspondence with this this particle processes from where this quin is natural. But
also, I wanted to ask, I mean, can you have slightly different, structures like a partition placed in some other way where quin win one is equal to the in win the other? I mean, that kind of thing have you looked at?
sorry, you mean the bijection?
Yeah, I mean bijection, but maybe with a related object. Maybe you somehow put a mirror there or something like that.
I mean, yeah, I
Did
don't know.
you try such things?
I mean, if you turn the diagram upside down somehow,
Yeah.
they start to look similar. All the gamma triples for them will become L triples for us.
Yeah.
But then, we don't know how to rearrange it back into Tableau. I mean, we tried various things.
Okay. That was very interesting.
It did not seem to work.
So, Arvind, you said as special cases, the McDonald's.
Sorry, I can't hear. Can you please speak louder? My volume is already maximum.
Oh, okay. Can you hear me?
Yes, now I can hear. Yes, sir.
Okay. I was saying, I mean, since you said that the McDonald polynomials are generalizations of Schur, Jackson, and all other polynomials. So, what does this translate into at the lower levels?
Oh, that's a good question. Well, first of all, these are these modified McDonald polynomials. Get these other fellows directly from P lambda is easier. So, for example, if you set Q equal to T, both Q and T vanish. Like you can see, they will cancel out, and you will get the Schur polynomial. If you set you set Q equal to 0, you will get the Hall-Littlewood polynomial. And jacks are more complicated. T to 1. So, but from the modified McDonald polynomials, I don't know how to do it. It's much more complicated. So you gain something, but you lose something. I don't know. There is a platistic version of Hall-Littlewoods, but I guess what are you looking for? Are you thinking of jacks or?
No, Hall-Littlewood polynomials are used in this general framework of Rogers-Ramanujan identities, which was recently done by Ken Ono, Ole Warner, and one more person. I think that paper is in Duke.
Okay.
So I was thinking along that lines.
Okay, yes. So there is a platistic version of Hall-Littlewood. So that you can get and maybe back transform to Hall-Littlewood. But directly getting these is hard. But as I said, there is a combinatorial formula for these P lambdas also using this A set, these multi-line queues due to these guys. Maybe you can use that to get Hall-Littlewood, but I did not think of it. Okay, so I should say, no, that's hard. No. So the problem there is that, No. Okay, I take it back. No, you can do it. I mean, the connection with the particle system happens at q equal to 1. Somehow q equal to 1 is very special, is important for this probability side. But they have a more general formula where I agree, you can set q equal to 0. Right. So yes, you can get Hall livelihoods from there. Yes.
Okay.
So it's this FIPSAC 2019 is there, and I think it's published in American Journal of Math.
Okay.
It's a very nice paper. So there they give the details.
Oh.
Yeah, and I mean, I know this, but it will take a lot of time to explain what it is.
Okay.
Yeah.
Sure. Thanks. Any other questions? If not, let's thank Arvind. Thank you, Arvind, for a nice one.
Thank you.